The research on education big data for students' academic performance analysis based on machine learning employs long short-term memory network (LSTM) to analyze educational big data. This approach efficiently processes time series data, allowing for the capture of time-dependent and long-term trends in students' learning activities. The study verifies the effectiveness of the deep learning method in predicting student performance by comparing the performance of different models. The analysis involves employment analysis, student specialty analysis, student development trajectory, online behavior analysis, and student portrait. The findings suggest that by analyzing educational big data, it is possible to make predictions about student behavior and potential risks, laying the foundation for providing personalized educational services. The research highlights the importance of using educational data mining to analyze and predict students' academic performance, particularly in addressing challenges such as weak self-control, lack of motivation, and internet addiction. The LSTM model plays a crucial role in dynamic adaptation within the education system, particularly in response to changing environments such as the start of a new semester, updates in course content, or shifts in teaching strategies. This adaptation is achieved by modifying the learning rate of the model or directly adjusting the model parameter W, based on update rules shown in equation 5. Dynamic adjustment not only improves the flexibility and adaptability of the model but also helps maintain its performance over long runs, especially when dealing with non-static data sources. By adjusting the learning rate, we can control the speed at which the parameters are updated during model training, affecting the stability and convergence speed of training. Learning rate decay is a common strategy to gradually reduce the learning rate during the training process to help the model converge quickly in the early stage of training and reduce the update step size when it is close to the optimal solution. Among them, exponential decay is a widely used attenuation method, as expressed in equation 6. EDNet-KT1 is a large-scale education dataset designed for knowledge tracking, which integrates data on the interaction of millions of students on online learning platforms. This dataset includes detailed records of student activity, such as clickstream, time of answers, correctness of answers, and more, and is designed to support researchers and developers in using machine learning models to analyze and predict student learning behavior and performance. EDNet-KT1 is data-rich and multidimensional, making it suitable for in-depth research on personalized learning, learning path optimization, and other areas related to educational technology. The experiment first involves data preprocessing, including data cleaning and feature selection, and the selection of key features such as correctness of answers and timestamps. Specifically, the model parameters are set to 128 LSTM cells, and a dropout rate of 0.5 to reduce overfitting. The training uses the Atom optimizer. The initial learning rate is set to 0.001, the batch size is 32 or 64, and the total training period is 50. Performance evaluation is performed through metrics such as accuracy, precision, recall, and F1 score, while k-fold cross-validation is used to ensure the reliability of the results. This comprehensive experimental design aims to provide an in-depth analysis of student behavior patterns in online learning environments and to evaluate the effectiveness of instructional strategies. The authors employed k-fold cross-validation to evaluate the generalization ability of their machine learning-based education big data model. This technique involves dividing the dataset into k subsets, training the model on k1 subsets, and testing it on the remaining subset. The process is repeated k times, with each iteration using a different subset as the test set, and the final result is the average of the k evaluation results. The authors presented the k-fold cross-validation results in Figure 3, showcasing the F1 score distribution across methods. The study concluded that the analysis of students' academic performance based on machine learning-based education big data demonstrates the effectiveness of multiple data science techniques and algorithms, such as KNN, DTW, and the author's method, in predicting and improving student learning outcomes. Experimental results revealed that advanced machine learning models generally provide higher accuracy and F1 scores, particularly in the case of k-fold cross-validation, where these models demonstrated superior stability and reliability. Furthermore, the application of different teaching methods and settings, such as traditional instruction, online learning platforms, and blended learning models, in data-driven decision support systems highlights the great potential of edtech solutions for personalized learning and student performance optimization. The findings underscore the importance of using big data and machine learning techniques in education to improve the quality and effectiveness of education. The study also identified areas that need to be further explored in future research, including algorithm optimization, data privacy protection, and the integration of multimodal learning environments. The authors referenced various existing studies in the field of educational data mining, highlighting the relevance of their research to the broader literature on student performance analysis and prediction.